Okay, yes, so I'll just skip this slide because you already said everything. It was just, yeah, a brief introduction about my background. My background is in applied maths, basically. And my research interests are split between three main topics, well, two actually main topics. So during my PhD, I studied the growth and morphogenesis of soft tissues. So my main broad field of research is the mechanics of soft tissues. So during my PhD thesis, I modeled the formation, for example, of these different patterns that we can see in the intestine. Using, yeah, it was mainly a theoretical job. Then I also did some numerical studies on this. I won't go into much details because my talk today is in a different area. Then after the PhD, I shifted a bit towards something more experimental. And I moved on to do some mechanical testing on soft tissues with the aim of characterizing mainly the elastic properties of the brain. And then, yeah, in the future, maybe I will focus also on other tissues, but well, that's what I've done so far. And also, so one part of the work was on, characterizing mechanically the brain, and then the other part was on model the behavior of the brain. So today, my talk is about the mechanics of the brain in rotational deformation, so in torsion. Okay. So why I call it twisted brains because of this. Well, it's a joke of words, but anyways, for me, twisted brains are all these situations, right, where the head gets a sudden rotation. So in the brain gets a rotational acceleration. Okay, so think about the lateral punch in the head or a car accident with a lateral impact where the brain goes on in rotation. Okay, this type of impact is supposed to be very dangerous, more dangerous than classical frontal impact, where the brain only undergoes basically compression, tension, or shearing. Okay, so rotational acceleration creates a kind of a scenario where that basically ends up generating more damage than a frontal impact. Okay, so the aim of my study was basically trying to understand a bit better the mechanics of the brain in torsional deformations. Sorry. What is believed to be happening at the cellular level in the brain during these impacts is a microstructural damage of the cells. So the cells of the brains are called neurons, and they have like a head and a tail. The tail is called axon. The axons are those units that basically transmit the signal between cells and allow the brain basically to function healthy. During traumatic events, what happens is that axon breaks, well, twists and then stretch and then break. So when this happens, the brain is functionally basically damaged, and because the transmission of signals is interrupted. Okay, this happens both in every type of impact, not only rotational impact. It's just to, give a bit of a explanation of what happens at the very bottom unit of the brain. Okay, as mathematicians, what we can do is to basically recreate an impact and try to understand where the most damage can occur in the brain after different types of impacts or different forces, different acceleration, different conditions. To do so, we build what are called numerical models, because analytically we cannot do much with it. But each numerical model would be a numerical model of the head and need to be fed with information on how each component works. This means find good constitutive models for each component of the head. So the brain, the skull, the membranes, everything. And to do so, you need to do testing of tissues. Okay, so that's a bit of the outline of what I have done. I took basically pieces of brain, put them into a machine, tested them, and then modeled the experiments. Get out the mechanical parameters of, so the mechanical properties of the tissue under such deformations, and then use them to simulate real head impacts. Okay, so to start, I have to say that soft tissues such as the brain are very complex tissues. So mathematically and also experimentally, they need to be treated with particular techniques, experimentally and mathematical fields. So the first big thing is that the brain is highly deformable. So it undergoes large deformation. So we need to account for that when doing the modeling. Then it's an incompressible tissue, so it deforms basically by keeping its volume constant. And yeah, it has a complex microstructure. The brain, in this case, is highly heterogeneous, so it's made of mainly two components, which are the gray and the white matters, which have different mechanical properties. Then, in general, soft tissues are also anisotropic. It doesn't really apply to the brain, and viscoelastic. So their mechanical properties are time dependent. So all these things should be accounted for when doing modeling of soft tissues. From the experimental viewpoint, there are two main techniques that can be used to characterize soft tissues. I'm going to focus only on the brain here. So the first is category is the non-destructive testing. So basically, this technique allows to test the tissue without taking it out from its natural state. So it uses basically waves. So you send a wave into the tissue, and then you record the speed. If the speed changes, it means that there is some non-homogeneity in the tissue, or the tissue can change stiffness, and that's how basically these changes in properties are measured and are captured. Yeah, then the other main type of test that can be done is the destructive test. Basically, for this, you need to take a piece of tissue and put it into a machine. So that's why it's called destructive. Of course, is maybe less truthful, but it still gives information on the mechanics of the tissue. So in the past, brain tissues have been tested in different deformation modes. So there's been people who have done tensile tests on brain samples. The problem with this testing, you can see it here on the left, is that even for little range of deformation of stretches, the deformation is non-homogeneous. You can see these bands on the side of the sample, which and the same happens for the compression tests, because the sample, even for little compression levels, it bulges out. Okay, so these deformations are non-homogeneous, and mathematically it's a bit more complicated to model them. Basically, analytically, it's very difficult to do any progress in that direction. You need to use numerical tools, so it's not very, yeah, it's difficult. And they also, the other thing, they give access to only one set of data. So if you do a tensile test, you will measure, you will apply the displacement, so the elongation, and you measure the force that is required to stretch the sample. Another test that is commonly done, less commonly but still done, it's simple shear. So in simple shear, you have a block of sample, you put it into two plates, and you move horizontally one plate with respect to the other. And in this way, you measure basically the shear force that is required to move the plate, and of course the deformation as well. Simple shear is a good test because it allows to reach high level of stretches, but again, it gives us access to only one set of data. So think if you want to, for example, if your model has more than one parameter, you will only have one set of data to estimate those parameters, which might give rise to non-unique solutions. So a good test should give you enough data to measure independently each parameters that you have in your model. So, okay, so that's why we did torsion, because the torsion experiment can be done into a machine that measures not only the torque required to twist the sample, but also the normal force that is required to keep the sample in place. So it gives us access to two sets of parameters. And because torsion is a global shear, it also allows to reach a wide range of deformation. Okay. Yeah, I already said this. So to do a torsion experiment, we use what is called the rotational rheometer, which was, well, we didn't have it at that time in NUIG, so we went to Dublin. So I went to Dublin and used that machine in University College Dublin. Yeah, as I said, torsion gives access to two sets of parameters. One is the shear, the torque, sorry, and the other is the normal force. Yeah, so there's a bit of disgusting pictures that comes after this as well. So the first step was to get the samples. Okay, in Ireland it's very difficult to get human samples. One main reason is because Ireland is so small that you might end up having in your hands the brain of someone that you know. So that's absolutely, yeah, not possible. So the other option, the closest option to humans is pigs, surprisingly enough. But yeah, so I went to a local abattoir and I got heads, pigs' heads, because in Ireland they don't eat the brains from pigs. They don't do the fry, the mixed fry, fritto misto alla piemontese. So they don't use brains. So that's good for scientists because we can use them. After 3 hours of hard work, you get a piece of brain which is, 5 centimeters by 4 max. And if you haven't thrown up at that stage, you can then go to the lab and test these tissues. I won't go into much details on how to open a head, but it's very hard work. Ecco. So from each little brain, we got maybe 9 samples. And we had, I can't remember how many, but I went to the lab many times for several weeks. At the end, I got a good bunch of samples. So when I say samples, they are cylindrical samples. They are taken from the different portions of the brain. The size, roughly, each sample was 10 millimeter high, and a radius of a diameter of 20 millimeters. Yes. Okay. I think in total I might have had 100 samples, something maybe less. But good samples, no, 100 is too much. I think I had less. But anyways, you will see at the end, the samples that actually were in which the test and the experiment went well were very, very few. So, yeah. So how does the protocol work? So we had those samples. We stored them in the fridge after the dirty job. We put them in the fridge and then we transported them into another lab where the rheometer was. But the samples were tested, let's say, in between 2 hours from when they were harvested from the heads. Okay, yeah. Then each sample was put in between the two plates of the rheometer, so was glued on the bottom with a high viscosity glue, and to the top as well. So the bottom and the top were glued to the two plates of the rheometer. Okay. And so the bottom plate is fixed and the upper plate moves up and down. So you can actually lower it up to the, down to the sample, then push a little bit and move the plate up again in order to, and wait for the force to be zero, basically, because you don't want any extra force applied at the beginning of the experiment. You need to make sure, basically, that the sample is in its natural state with no pre-compression, nothing. That's why we checked before starting the experiment that the normal force was value 0. Then in the rheometer, you can set the rotational speed of the upper plate and the length of the test. So how long do you want the plate to rotate for? So the tests were done at a constant speed. Yeah, that's it. And we measured the torque and the normal force. So what happens in the experiment is this. So I'm gonna have to exit the presentation and I'll show you the test here. Okay, so you see at some point the plate will start rotating and then, yeah, the sample breaks. But in the meantime, you know, I'll play it one time again. Okay, at that point, the normal force is 0, then the plate starts rotating at a constant speed, and we record the normal force and the torque. Okay, sorry. Okay, so I'm going to show you now some outputs of and inputs of the rheometer, just to understand what kind of data then at the end we work with. Okay, so this is the graph of the plot of the velocity, so rotational velocity with respect to the time. So you see that, okay, so the velocity is expressed in terms of this twist rate. So it's the angle, the rotational speed, so the rotational, the omega. That's it, yeah, divided by the height of the sample. The speed, okay, let's call it just speed, not to complicate the matter. So you can see, okay, there's an acceleration phase, which is the black part of the curve. Then there's the purple and the orange part of the curve. That's basically when the speed reaches a constant value, okay? That's when the range that we are interested in, the purple and the orange part, okay? Because what happens before is just an acceleration phase of the rheometer before the plate starts rotating at a constant speed. So remember, the black part is not of interest, the purple and the orange are of interest. Now I'll tell you what they mean. These are the plots of the torque versus the twist and the normal force. So torque versus twist and normal force versus twist squared. So the twist is the rotational angle of the plate divided by the height. So it's a measure of the deformation. The torque is the torque, and the twist square is the square of the twist. I plot the normal force versus the twist squared because, well, just to show that it's linear in the elastic region, which is the purple one. So yeah, let's explain this region. So remember, the black part is the acceleration part. Okay, so we don't really care about that because, yeah, we want the test to be at a constant speed. We want to look at the basically the elastic regime, so we need to be in a quite static condition, basically. There is the purple region. Then something happens, and then there's a dramatic change in the trend of the curves. That point up there and down here is the breaking point of the sample. Okay, so everything that happens after that is not elastic anymore. Yes.
That's my question. What are you controlling? You're controlling the area of the sample, which is fixed.
Yeah.
And you apply the force, which is negative. It means that you are.
No, wait.
What does it mean? And zeta the force, right?
Yeah, but that's measured.
That's measured.
Yeah.
Yes. That is the one that you need to keep the area.
Yes.
Okay, what does it mean? It's negative.
Yeah, I'll tell you. Yeah, in a second. So what we impose is the rotation, so the twist. Okay, we make the sample to twist, and then we record the forces and moments involved. Okay, so these are the outputs, and this is the input, the twist. Okay, yeah. So the normal force is negative. It means that there's a compression on the sample vertically. So it means that the sample is trying to push up when it's twisted. This is a phenomenon that is typical of nonlinear material. It's called the pointing effect.
Isn't it actually also normal material? You don't have a
you
don't have a circular lever. When you twist it, it goes up.
Yeah.
So if you keep the height fixed, you always have compression, right?
Okay, yeah.
As soon as you have a non-circular section.
Yeah. Yeah, it's a nonlinear effect. I think
Well, also linear.
but I think it's geometrically nonlinear.
It's called funzione inglobato.
Okay. I know it is pointing effect.
It's also in linear enough.
Yeah. That's okay. Yeah. Okay, so basically from these two plots, what we have to retain is that the torque is linear with respect to the twist in the elastic region, which is the purple one that we are interested at. And the normal force is again linear with respect to the twist square, and it's negative. Okay, these are the key things that we have to remember from this picture. Okay, that's the, okay, basically because the normal force is negative, it means that the sample is trying to push up against the plate. And this is called the positive pointing effect. Okay. Yes.
Are you also mentioning the radius of the sample with time?
No.
No. What's your impression? It's growing or getting smaller? Maybe same.
I think, well, the thing is that it is, if it was pure torsion, it should stay the same. But there's something that it relates to the experiment. Basically, at the beginning of the experiment, yes, we made sure that the normal force was 0. But in gluing the sample, there's some kind of, you glue the sample, you push down the plate, you lever it up, you leave it there, and then you press the play button. The normal force is not 0 anymore when you press the button, because there's some viscoelasticity, some relaxation, something makes the sample to, relax. That means that there is a pre-compression in the sample anyways, most of the time in the samples before starting the experiment. This causes the radius to shrink a little bit. But we didn't measure it because we didn't have any, you need to place a camera and then try to figure it out with that. We didn't have it.
And probably if you glue the sample, you also affect the possibility of the material to change the radius.
Well, yeah, at the edges, yeah, the radius won't change, but in the cross, yeah.
The way it breaks,
The
the way it breaks.
Yeah.
It actually seems that it's put traction.
Interaction, what do you mean? Rather,
No. I mean, according to the movie, but probably I get it wrong. But if I recall the movie,
yeah,
the way it breaks,
Yeah.
the way the sample breaks, would make me think of attraction.
but in fact, you see, when the sample breaks, the normal force goes up, so there is some kind of.
Okay. So first it is contracted, compressed, and then.
Yeah.
Okay.
In its elastic behavior, it is compressed. Then when it breaks, yeah, well, the normal force increases. So, yeah, and that's possibility that, you know, goes towards tension, traction. Tension. Yeah. Yeah. So in the end, the good tests were only 9 after all this. But we were happy with 9 samples.
What
Yes.
do you mean with the good test? What happens with all the others?
The others, either they break too early, either, you know, there's too much uncontrollable effects for which the results are non-consistent. Yeah, mainly this.
Do you track where the samples come from? So if they came from the same brain, this 9, or
Well,
they came from different ones?
Yeah, that would have been a really nice thing to look at, but because we didn't have enough samples, we couldn't. But yeah, definitely, that is a interesting thing to look at. Yeah. Okay. So this is just the the collection of the good samples. Let's call it like that. That's the torque versus the twist for the 9 samples, and this is the normal force versus the twist squared for all the 9 samples. Okay, so basically from this section, what we have discovered is that the brain in torsion displays the positive pointing effect. So it tends to expand vertically, so push against the plate. That's why the force is negative. The other interesting thing that we managed to do is to quantify this force, this normal force, because in simple shear, there's no commercial device that is, that you can buy from a company like for the Rheometer that measures both the shear and the normal force. But with the Rheometer, you can quantify basically the pointing effect for any tissues. In this case, we did it for the brain. Okay, so now I'll move on to the modeling of the experiment. Okay, so I didn't know how many of you were familiar with the theory of continuum mechanics, so I did a bit of introduction on that. So, to model the mechanics of the brain in torsion, we use the theory of continuum mechanics, in which basically we treat the sample as a solid body, and how do we write the equations that govern the deformation of a continuum body? We need basically these 4 key elements. We need the kinematic of the deformation, the balance laws, in this case, just the balance of linear momentum if we want to simplify things very, very much. The constitutive equation, which tells us basically how the material behaves. I'll go into more details, and the boundary conditions to close the problem. Okay, so let's write down the deformation. Because as I said earlier, soft tissues are highly deformable. Then we need to use the theory of large deformations, for which basically we define an initial reference state where the tissue is in its undeformed state, and then a final deformed configuration where the tissue has been twisted in this case. How do we go back and forth from these two states? Is basically like with the change of coordinates. We define the coordinates in the reference configuration with the capital letters, so big R, big theta, big Z, and the coordinates in the deformed configuration with the lowercase letters. Okay, so how do we write down the deformation? Is with these basically three equations where little r, little theta, little z are the deformed coordinates, so the points in the twisted configuration. Lambda is the little pre-stretch due to the gluing process, basically, and phi is the twist. So the rotation, the angle of rotation divided by the height of the sample. Then the balance equations, they reduce to, I simplified here, so to the balance of linear momentum, where we have basically the main equation is the divergence equation with the boundary conditions. So divergence of sigma. Sigma is the Cauchy stress tensor, which is a matrix with 9 components. So we have 9 unknowns in this system. And we have one boundary condition, which is on the radial stress. That translates basically in this way. There's no traction on the lateral surface of the cylinder, so the radial stress component at the outer radius is 0. So the divergence of sigma equals 0. Sigma is a 3 by 3 matrix, so is a tensor. The divergence of sigma is a vector, so with 3 components. Three components. I say it in with the Irish way. 3 components. So we have 3 equations, 9 unknowns. How do we work out this? How do we reduce the unknowns? With the constitutive equation. Here again, I didn't know how familiar you were with the continuum mechanics theory. So the constitutive equation basically is the equivalent of Hooke's law for the spring. Is a function that relates the deformation to the basically the deformation to the force applied to the body, if you want. For the spring is a linear relation between the force and the displacement, and the coefficient is that links these two quantities is the stiffness constant, K. In a nonlinear elasticity, the constitutive equation is something a bit more complicated that relates the stress to the deformation. And the link between the stress and deformation are the mechanical parameters, elastic parameters, because here we are just treating elastic bodies. So here we did a couple of assumptions. The first one is that the solid is hyperelastic, so you can basically write the constitutive equation with respect to an energy, the strain energy function W, which is a function of the deformation through F, which is the gradient of the deformation. Anyway, the other assumption are that we assume the brain to be isotropic and incompressible. So incompressibility gives rise to this P to the constitutive equation up here, Lagrange multiplier, and that's the strain energy function, as I was saying earlier. The other thing that now comes from the other hypothesis that now comes from the experiments is based on the observation of the relation between the torque and the twist and the normal force and the twist squared, okay? Because these two relations are both linear. In continuum mechanics, the simplest constitutive model that gives rise to this type of behavior is the Munir-Rivlin model, which is basically choosing a form for the strain energy function in the form of a Munir-Rivlin strain energy function, which is this one here. That depends, so F again is the gradient of the deformation. The main thing here is that depends on two parameters, constitutive parameters, C1 and C2. Okay, this, yes, one. Okay, basically substituting W into the constitutive equation here, you get this final constitutive equation. Okay, so you have a relation between the stress and the deformation. Here is the tensor B, is the left Cauchy-Green strain tensor, if I remember correctly, which is a measure of the deformation, and it depends on these two parameters, C1 and C2. Okay, now, just to go back to the main formulation of the problem, we have the governing equations with the, yes. Okay. Okay. So we have the governing equations, so the divergence of sigma with the boundary condition on the radial stress, which is 3 equations with 9 unknowns. Then we have the constitutive equations, which basically we can plug into the divergence of sigma, and we end up with basically 3, no, we end up with one unknown only, which is the Lagrange multiplier, because B is given by the gradient of deformation, which depends on the deformation here. So everything here is known because the lambda and phi comes from the experiments. Yeah, at the end is an ODE, simple ODE in one variable P that depends on little r. I don't know if you can see it. I guess, yeah, it requires a bit of calculations, but at the end, it's the good thing is that we can solve it analytically. We don't need to do any numerics or anything. And once we find the Lagrange multiplier, we substitute it into the constitutive equation, and we get the components of the Cauchy stress sigma. Yeah, from here, so from the shear component of the stress, sigma theta z, yes, up there, here, and from the normal components of the Cauchy stress, sigma zz, we can analytically work out the equation of the torque and the normal force, which are the quantities that we measured in the experiments. Okay. You see that by doing the calculations, what we get is that the torque depends linearly on the twist, and the normal force depends linearly on the twist square, plus a constant, but still linearly. Okay, which is the same behavior that we observed in the experiments. Is it clear so far? Okay, good. So now the only things that we don't know are the two parameters C1 and C2, which are the elastic parameters that characterize the brain. And by doing some model fitting from the data, we can work out the coefficients A, B, and C. Yes, because the torque, remember, the torque, the slope of the torque versus the twist is the coefficient A. We can get it from each sample that we tested. Same for the normal force. The slope of the normal force with respect to the twist is the coefficient B, plus C is the offset given by the precompression. Okay, so by doing the fitting from the data with these two equations, I have them here. Yeah, we work out the coefficient A, B, C, and then by reversing, yeah, by reversing, well, we know how A, B, and C are linked to the constant C1 and C2. Yeah, because from here, yeah, this would be the coefficient A, this would be the coefficient B, and this would be the coefficient C. So we can calculate C1, C2, and the pre-compression lambda. Okay, we can do that for all the samples, and we end up basically with an estimate of C1, C2, from which, you remember, 2 times C1 plus C2 is equal to the shear modulus, mu, here. So we basically estimate mu and the parameter C2 for each of the 9 samples. And here are all the data. Here are the coefficient of determination that tells us how good the fitting of the model with the data is for each sample. And the closer to 1, the better the fitting. So basically these values in these 2 columns tell us that the fitting was actually pretty good and so accurate. Okay, and what we have at the end of all these experiments and modeling are basically the 2 parameters, mu and C2, that we have estimated from our torque and normal force from the experiments. Add that we compare them with the estimation of the shear modulus from simple shear experiments, and it actually is in the same range. Okay, so that's another extra validation. Okay, so from this section we have another 2 good things. One is that we were able to estimate shear modulus and the second Mooney-Rivley parameters, C2, which is the one linked to the pointing effect. And we found out that in torsion, the brain behaves as a Mooney-Rivley material. Okay, the same result was obtained in simple shear, basically that the brain behaves as a Mooney-Rivley material in simple shear. It's not too surprising in the sense that because simple shear and torsion are very similar deformation. If you think about it, simple shear is a local torsion. Yeah, each point on the outer surface and in torsion undergoes shear. So that's good. Everything is consistent. Okay, at the end, we did some, so to further validate our modeling approach, we also did a finite element model of the experiment. So we built a torsion, the torsion of a cylinder in Abacus, which is a finite element software. And we simulated the torsion of, in 2 cases. One case was simple torsion, the other was the torsion with the pre-compression. And we compared the results, again, of the torque versus the twist and the normal force versus the twist squared, obtained from the numerical simulations with those obtained analytically. You can see the triangles are the numerical results. The line is the theoretical modeling, and they match. And of course, the dots are the experiments. Okay, this is the graph for the plot for the normal force. So here, there's a bit of a difference between the numerical model and the analytical model. We think it's because, remember, the compression creates a little bulging. So analytically, this bulging is not predictable, but numerically, yes. So that's why there's this little difference between the theory and the numerical results. Here is just the video of the simulation. It's not really interesting. I can show you though, because you can see the little bulging. Oh, I have it somewhere else. Actually, sorry, 1 second. I can play it from here. Yeah, you can see that as the cylinder is pre-compressed, there's a little bit of bulging. Yeah, that's what probably causes the difference between the numerics and the analytical solution. Okay.
Perhaps the logic that you get, no, I don't know, right?
Yeah.
But perhaps,
Yeah.
perhaps this description, in fact, with the imposed information you show us, is perhaps not consistent with the logic. Because if you keep the lower circles fixed, you may have another mechanism. I mean, the deformation is not so simple as the one. But this is a question. Because you impose a deformation which is rather simple, right?
Yeah,
You
in
have-
the analytical model.
In the analytical
Yeah,
model.
yeah, yeah.
Whereas in principle, we should have a complete boundary of problem.
Yeah.
Zero.
Oh, yeah, no, that's exactly what.
Okay.
Yeah. Yeah, because the finite element code can
Sure.
account for all the edges effect,
Yeah,
everything. So,
Absolutely.
yeah. But at least it's not too far from the analytical solution. Yeah. Okay. Then at the end, what we did, so far we were able to, well, first find out that in torsion we can use a Muni-Rivlin model to model the elastic behavior of the brain. Then we had the two coefficients in the Muni-Rivlin, in the constitutive equation. So we put this information into a finite element model of the full head. So we inputted for the brain components, we used the constitutive equation given from the Muni-Rivlin model with the parameters that we estimated from the experiment. And we simulated a rotational impact. Basically here, what we see are three different sections of the head. Well, we are actually only looking at the brain. And we show basically the normal stress and the shear stress components distribution in the brain. And we see that, first of all, the normal components, the magnitude of the normal component is in the same order of magnitude as the shear component. So this tells us that the normal forces might contribute into generate some damage in the brain as well as the shear forces. And and then also we picked an acceleration that was taken from some tests that people have done on actual test of head impacts, of helmet impacts as well. And we show that for this range of acceleration, the level of magnitude of the forces are in the same range of dangerous levels for brain damage. Okay, the good thing is that because we were able to, so the constants and that we use in the brain were calculated from actual torsional experiments. So these are supposed to be a bit more accurate than just general, constant estimated from other type of deformations. Okay, so that's it. Just to recap, the main thing from this study is that we propose a new protocol to test brain samples in torsion. Is a good protocol because it gives access to two sets of parameters from which we can estimate at least independently two mechanical constants. We measured the pointing effect, which hasn't been done before, and we confirmed that, we confirmed that the brain behaves as a Muni-Rivlin material in torsion as well as in simple shear. So next step that I hope to do in the future is to do experiments, so use the same protocol basically to investigate the viscoelastic properties of the tissue. So I have a collaboration ongoing with the University of Manchester on the theoretical part. So hopefully that's next step down the line. That's it.